finish that problem with triangular loading? Did we find the maximum displacement?
Yes.
Good, okay. So what I'm going to do today is do this. Do that, you will see that's what you get. You get a function that looks like this. That would be something like this, okay? So this plot, as you can find, that is quite useful. For instance, of course, this is the generalized plot, right? For something like this. For our particular problem, we had T0 was 0.03, T, which is the natural period, over omega n. Omega n was 34.05. So this one was 1 point, actually that was, okay, I think that was, yeah, this comes out to be 0.1845, okay? So, I'm sorry, yeah, that. So if you evaluate T0 over T, that would be 0.163. So if you plot a curve like this, you can see that for the value of T0 over T, that is 0.163, the maximum value of the response would be 0.5, or this value would be 0.5. Or in other words, what this tells you is that if the duration of the load is such that T0 over natural period is 0.163, the dynamic response will be only half the static response, right? If this is, for instance, 0.4, you see that dynamic response would be equal to the static response. In other words, a plot like this gives you a very good feeling that the response, the dynamic response of a system under generalized loading, it really depends on T0 and the natural frequency. In fact, in this case, as you can see, if, for instance, this is 0.8, is where you have the largest displacement. But once you pass, say, certain value, I don't have exactly that, but I think it's about 1.8. In other words, if you pass the value of time, duration of time, 1 point over the natural period, 1.8 or longer, the response basically would oscillate between these two bounds, where this is 1.25. In other words, no matter how large the duration of the time is, the maximum dynamic response cannot exceed more than 25% larger than the static response. So this response spectrum not only gives you a good tool in order to find the maximum displacement or maximum response, but also shows you that clearly how this response is a function of these two functions. And necessarily, when you have a dynamic load of a general form, doesn't mean that the effect would be more severe than the corresponding static displacement. Because the sort of the, at least intuitive or the common perception is that if you're told, oh, the system is subjected to a blast loading, wow, that must be a very severe situation, so we should design for a factor of safety of 2 or dynamic load factor of 2. That is only applicable to the case of impact load, not necessarily any type of general loading. For any general loading, you need to plot this response spectrum for these various shapes of the input signal or wave in order to find the maximum dynamic response. But overall though, be aware that is a function of these two. Okay? I'm going to do another example to set up, in fact, the shock spectrum in much more general terms that gives you a good appreciation of what shock spectrum is all about. So let's do this problem. Let's say we have a loading function that looks like this. One of those given in that table. So you have a load that between time 0 to some time, it is a ramp load, then from that point on, it stays constant. And what you want to do is you set up the shock spectrum for a single degree of freedom system subjected to this load. Shock spectrum is mainly used, in fact, for complex system, multi-degree of freedom systems, but as you will see later when we start multi-degree of freedom, any multi-degree of freedom system can be, in fact, reduced to decoupled single degree of freedom system in terms of the normal modal coordinate. So for each of those, you can consider a shock spectrum because it's a single degree of freedom system, and then find the effect overall on the system. But so the concept of shock spectrum is very useful when it comes to general loading. So let's do that for this problem. Of course, I'm not going to solve the Duhamel integral in its general form, which is 1 over m omega n f tau, in this case, sine omega n t minus tau d tau. I just go to the table that I have and look at when I have a forcing function like this, which is what? Which is f, which is given as f0 over t0 tau when t is greater than 0, less than t0, and then it is constant when t is greater than t0. And I look at the table and I see that the response for both of these cases has been tabulated. So this is from that table. For case when this load still is acting, the ramp loading is acting, is U is F0 over K times T over T naught minus sine omega n t divided by omega n t0. So this is the response for case 1. If you look at that table, I believe instead of f0 over k, I have f0 over omega n, something like that. But that might be right, actually. But anyway, that's for the case 1. For case 2, if you look at it, u of t is f0 over k times 1 plus sine omega n t minus t0 divided by omega n t0 minus sine omega n t over omega n t naught. So what I want to do is we want to plot maximum u versus t0 over t. Okay, that's what I want to do. How do I find u max? We know basically that we need to take the derivative of this, find the time, substitute it back into that, gives you a function that would give you the maximum u, right? So let's do that. So in other words, I need to take du with respect to t is equal to 0. This will give me t peak In other words, the t corresponding to the maximum value, where that would be maximum. Okay. So I would assume that the maximum displacement will occur somewhere here, beyond this. So in other words, I would say that this is where the maximum displacement would occur, which is usually the case. So I would assume this is where the maximum would occur. In other words, at t greater than t0, okay? So if that's the case, I will take just the derivative of this, and that will give me omega n over omega n t0 cosine of omega n times t minus t0, okay? Oops, I better write it like this, that's better. So omega n times t minus t0 plus omega n over omega n t0 cosine omega n t. So I just took the derivative of this. I want to equate that to 0 to find the maximum, the time corresponding to the maximum u. So if you rewrite this, you will get, you simplify that, you will get cosine omega n t, cosine omega n t naught, plus sine omega n t sine omega n t naught is equal to cosine omega n t. I just expanded this, that's all. Okay. Now, if you divide by cosine omega n t, okay, what you get, and do some trig manipulation, you get tangent of omega n t is equal to 1 minus cosine omega n t naught divided by sine omega n t naught. But what is this time? I call that t of p. In other words, if I find t of p from this, right, substitute that into this equation, that will give me the u maximum. And that's what I want to do. How do I do that? We know by now that's not easy. So we have to find an alternative way, okay? So how do I do that? I would say that basically, if that t of p, okay, we just make the assumption, would be at t naught. In other words, let's assume maximum displacement occurs right here. If that is the case, okay, what it means that you need to substitute for t0 in this equation, right? So if you do that, what you will get is going to be 1 over 0 plus cosine omega n t over t0 is equal to 0. So what I said was, I'm assuming that t0 is the maximum value, is where the maximum displacement occurs. So I need to substitute t, which is t0, in this equation, and that's what it will give me. So from here, if you solve this, you will see that what it gives you is cosine omega n t0, okay, is equal to -1, or omega n t0, which is that tp, is equal to pi, okay? So that means tp, okay, is going to be pi over omega n, okay? But we do know that or actually I would just leave it as that, that's better. We do know that maximum displacement does not occur here, but at somewhere beyond that, right? So in other words, it will occur somewhere, or maybe I would write it down here, TP is. It will occur at somewhere that the actual TP would be larger than this, okay? Or in other words, basically omega n TP is going to be larger than pi. So if omega n dp is going to be larger than pi, okay, here we're looking at the unit circle, okay, this is the tangent and this is cotangent curve. This is sine, oh, this is cosine axis, this is the sine axis, right? So if it is larger than that, right, that means tangent is going to be positive. And I think you need to refresh some of those trig courses that you took. So that means that tangent function can be basically, which can be converted to sine and cosine. Maybe I will write it for you. Sine of alpha is tangent of alpha over plus and minus 2, no, actually 1 over 1 plus tangent squared alpha from trigonometry. So if this is larger than pi, these two would be positive. That means we consider only a positive sign. So evaluate sine of omega n TP would be negative times 1 minus cosine omega n T0, okay, over 2 times 1 minus cosine omega n T0, and cosine omega n TP would be negative sine omega n T0 over 2 times 1 minus cosine omega n T0. So sine actually would be, okay, negative cosine. So that's basically what we get from here. So all we are trying is to find time at which the maximum value occurs. And this is the time. So what now we need to do, substitute those back into this equation. In other words, you expand this, you know that sine of omega n t, for that you would need to substitute sine of omega n tp, right? Because time now is the time at which this is maximum. So these are the values of time that you substitute in this equation to get this maximum value. Okay? So if you do that, you get basically maximum value, which is from there, would be, which is u at t is equal to tp, would be f. If you simplify that, you get this relationship. 1 plus 2 square root of 2 times 1 minus cosine omega n t0 over omega n t0. This is u max. So if I can summarize that, you just derive the displacement response, take the derivative, equate that to 0, find the time, which will be the time at which the response is maximal. You cannot find the time directly. You can find a trigonometric function of that time for maximum value. Substitute that back into the original equation by doing some identity tricks, and this is basically what responds. Okay? This is all we care about. If you plot this function now, which looks like this, in other words, if you plot this function, I plot that as t0 over t, okay, versus this u max, okay, you get something like this. This is 1, this is 2, you get, okay, 1, 2, 3, 4. This is what you get. This is the response spectrum of that system under the action of this law. In other words, this plot is a very useful tool that gives you the maximum dynamic displacement versus time duration. Let's look at it. For instance, if time duration t0 is 0, your forcing function would be something like this, right? But what is this? This is an impact load, right? So t0 is equal to 0 is right here. So that means under an impact load, your dynamic displacement is twice that f0 over k. That's what this curve gives you. If you have, for instance, t0 over t is equal to 1, in other words, if t0 is equal to the natural period of the system, as you can see, the maximum displacement would be equal to the static displacement. If it is 1.5 or 2.5 and so on, okay, the maximum value of the response would be about 1.25 times U max, or 1.5 f0 over k. Okay. So this is a very useful tool. Plotting the shock spectrum gives you the ability to evaluate the response of the system on basically in a wide range of time responses with, signals with different time durations. This is very useful actually in cases like blast loading or earthquake loading, when you are given basically, this allows you to estimate what the potential maximum displacement would be. If the time duration is such, that's what would be the maximum displacement that I should be expecting. Of course, this is a very, very brief and quick overview of shock spectrum, but remember that in the case of generalized loading, what is analogous to the frequency response function is the shock spectrum or the response spectrum, which is the plot of the maximum response versus a normalized time duration of the applied load. Okay. So with that said, we are almost there, but let me just, quickly also cover one topic. We're not going to discuss it, of course, in this course, but it's important for you to know. And then hopefully we will bring this whole discussion on single degree of freedom systems to a closure. So the last and final topic, and I'm just going to glance over that, is numerical integration. Needless to say that if the forcing forcing function is not one of those given in that table, or is a weird general type forcing function, which, or maybe a set of data that you have collected that represents the excitation of a system under the action of those. How do you find, in general, the response of the system? In Duhamel integral, right, using Duhamel integral, to find the displacement response, this is the function you have, right? If you have undamped system, this is what you need to evaluate, right? Or if it is a damped system, this would be what? 1 over m omega d, integral from 0 to t, f tau, e to the minus zeta omega, and t minus tau sine omega d, t minus tau d tau. Obviously, this is the most commonly used one because for the damped system, especially given the system with low damping, we don't want to go through an additional hassle of evaluating a more complex integral. But nevertheless, let's look at these two, in fact, integrals. So let's take a close look at this. What do we have here? We have this sine function, which I can write is its trig identity, which is sine omega n t cosine omega n tau minus cosine omega n t sine omega n tau, right? So this integral is basically, it consists of two separate integrals. So I can divide it into those two parts, which would be m omega n tau, okay, integral from 0 to t. Since the dummy variable, or the variable of integration is tau, right? Sine of omega n t is a constant, comes out of that integral. So I have basically f of tau cosine omega n tau. Same thing with this one. I have cosine omega n t integral from 0 to t f tau sine omega n tau d tau. So now let's take a closer look at this. If I call this A and this B, right? Duhamel integral is reduced down, evaluation of it, to this, right? A sine omega n t minus B cosine omega n t, right? And we know this can always be written as a single harmonic function, right? So in other words, this is a squared plus b squared sine of omega n t plus this phase. But what does this tell me? That solution to Duhamel integral, right, is a harmonic function whose amplitude and its phase obviously is a function of these functions, or the time function that represents basically this Duhamel integral, right? So in practice, okay, in practice, all we have to do, as long as we have the dynamic characteristics of the system, meaning the mass and natural frequency, all we have to do, numerically evaluate these two integrals. And that's what we do. Of course, we are not going to discuss how. If you want or you're curious, You probably can even use some MATLAB toolbox for evaluating any function, doesn't matter what function is. If you're given the function, all you need to do is just set up this integral, use the MATLAB toolbox for numerical integration, and find that, right? And there are several algorithms for doing that numerical integration. The most common one is numeric, beta, and Wilson, theta, and there are several other algorithms that you study that in any numerical analysis or say finite element course if you take it later on. But that's what in practice we do. We are not crazy to go over, use all those tables and do all those longhand calculations. Those are just for you to see sort of fundamentally where these came from. But that's in practice. So even in the final, which I will give you a Duhamel integral, maybe proving one of those, say, responses from any of those tables. If you prefer, in fact, I do encourage you, just use maybe MATLAB and derive the response. In fact, I prefer that because that way you can see the benefit of numerical integration of the general approach that these analyses are done, okay? So with that said, we say goodbye to single degree of freedom systems. So the last 2 weeks, we're going to focus on multi-degree of freedom. It's not a lot, it just gives you at least an exposure to some of the fundamental concepts in multi-degree of freedom system, such as what is the shape function, what are the mode shapes, what are the natural frequencies, what are the modal coordinates, and so on. We'll discuss all of those so you get at least some appreciation for the multi-degree of freedom.